Welcome to our SEAM studio here in the heart of the Free State in Bloemfontein. This channel serves to bring you only the best in aviation safety. Join me now as we cross over to one of our aviation experts, Charlie Murray.
Our greetings here from the SEAM studio to one and all, and welcome to the next series of 5 deliveries in stalling. We've seen that so many accidents happen because, well, I believe it is because we don't all 100% understand why and how stalling takes place. And if it takes place, what do we do? How do we recover from that? And that is what I'm going to cover in the next 5 presentations. However, when we're ready, let's go for presentation number 1. First off, let's have a look at the lift formula. For those of you that probably don't know, lift equals the coefficient of lift half rho v squared f's. In other words, the lift is what is produced on top of the wing, lift, which has to oppose weight, and lift is dependent on coefficient of lift or rather the angle of attack then, if you want to put that, because the coefficient is dependent on the angle of attack, half the density, which is a constant and that is not considered a variable in this formula, velocity square, how fast we're going forward, squared, all right? In other words, that is the second variable, and then the size and shape of the wing itself, which is going to be considered to be a constant in this case. We are not going to look at variable wing sizes and wing shapes, so the first deliveries are going to be, in fact, without flaps as well. Right. The next step would be to find V in the formula. Remember, we had lift equals the coefficient of lift half rho v squared s, and now you can see that it has just been thrown around, and if you work it out, the v now becomes isolated, the square goes over into the square root on the other side, right? So it's moved over this side there over the lift, as you can see, and then your coefficient of lift and half the density and s moves right at the bottom. Okay, what is important in this formula is that you can see that lift is now being isolated. So the velocity on the one side, square root, if lift is the one that increases, if your angle of attack, let's say, it will obviously change depending on the speed and how, if you do any maneuvering, the density normally, this will stay a constant, and for now the s is going to stay a constant as well. So here we play v equals the square root of lift, which is the one variable, and the coefficient of lift, which is the other variable. Right, let's carry on. It is a good thing. We'll have to look at the stalling speed, and the stalling speed, the formula that I'm going to use is according to the AP3456A, which is what the British Air Force is using, and as far as I'm concerned, that's probably one of the most accurate, or the most accurate, let's say, definition out there. But let's demonstrate what it says. It says, when an aircraft, now remember the aircraft is of stated weight, the weight is not going to change. And in clean configuration, in other words, if the undercarriage is down, it will stay down and locked if that is, okay, let me rather say, if it can retract, it will be retracted. If it can't, it's down and welded. Leave it there. Oh, it's not that you can do anything about it, is it? All right, flaps up. And that is when an aircraft, in other words, of clean configuration, when the engine or engines are throttled back completely, So the idea is now that you must maintain straight and level. In other words, directly in your path, you're not allowed to turn, and you're not allowed to climb or to descend. So as the speed reduces, you will have to increase the angle of attack, increase the angle of attack, increase of the angle of attack, until you reach an angle of attack where the aircraft can no longer maintain straight and level. And we're interested in that point where the angle of attack reaches the critical point where beyond that there is a serious deterioration of the development of lift by the wings. Right, so without further ado, let's go to the next slide. The definition of VS. Now, I've got to make this point immediately here that if you go to the A3456A, you will find that they're talking about VB, and the B is then for the basic stalling speed. Now, depending on where you are in the world, they will talk about VS or VB, sometimes VS1. But for now, when I'm talking about VS or VB, I'm going to take that these two are exactly the same. In other words, just hang in there with me. So I say the limit the limit of the green arc on the VSI, and I'm going to show that in the next slide. The stalling speed or the minimum steady flight obtained in a specific configuration. For most aircraft, this is the power off stall speed at the maximum takeoff weight in clean configuration. Gear up, if retractable, and flaps. All right, I think we have worked through this definition now, because remember, we want the basic stalling speed. Not anything beyond that. We'll get to the maneuvering stalling speed. For now, it's just the basic stalling speed. But without further ado, let's get on with the next slide. And here, we're now going to have a look at the airspeed indicator, and we're going to start off here with looking at VS, the V stall. All right, that's the stall speed minimum, and we've now actually talked about this one quite a lot. Bottom of the green arc, that is the first point that we are interested in, and then the next one that we're interested in is the VSO, and that's the stall speed, minimum flight speed in landing configuration. In other words, the undercarriage is now down, whether it's a retractable or non-retractable, undercarriage is down, and then it's landing flap. Now remember, all these speeds, or these two speeds, are determined with power closed. Right. The next one that we are looking at here is then the VFE. That's the maximum flap extended speed. Remember now that in some cases you will actually find that the first flap selection in some aircraft coincides with the maximum speed that you may deploy the undercarriage. So don't get confused with this one now. We are here talking about all the different flap settings, and normally the white arc is the one that is important for us there. Right, and then we've got VNO, maximum structural cruisal speed of maximum speed for normal operations. Does it mean you can fly at a higher speed? Yes. But remember, the moment that you start flying in this arc, you actually don't want to do hard maneuvering, and then, unless obviously the aircraft is stressed for that. But for now, they say the maximum structural cruising speed, maximum speed for normal operations. Good. So, next slide. Now it's time to look at the basic stalling speed. Let's start off to say, where are we going to get this basic stalling speed? And the first thing, remember, when we are flying straight and level, if the aircraft is properly trimmed, everything straight and level, cruising power and all that, lift equals weight. If you now take the power away, the aircraft tendency will be to nose pitch down, and as the speed reduces, you will have to actually increase the angle of attack as the speed reduces, and that is simply to satisfy lift equals coefficient of lift half rho v squared. In other words, as the v square comes down, you've got to increase the angle of attack, and that obviously can only be true up to a certain point. And so if we look here, that in straight in level, you'll find that in straight in level, lift equals weight exactly. Now, Now this is the one that we must understand. Anything else, in a climb, in a descent, in a turn, in anything else than where lift is exactly the same as weight, everything else we talk about maneuvering. I'm not talking about momentarily going through that when you do aerobatics. No, don't get to that point. What I'm just saying is that straight and level, lift equals weight, period. Anything else is maneuvering. So now we say, because lift equals weight, and weight is a constant, you're going to just now say to me, yeah, but what about when you pull G's, the weight increases? The weight stays exactly the same. It is the apparent weight, and we're not talking about this. For now, we're looking at a formula where the weight is a constant. In other words, what we've got here is now a constant. And the moment we put then, we can say it's Vs, and in some cases we talk about Vb, the basic stalling speed. All right, but we're over that one. And in all other cases, lift will either be bigger or smaller than weight. And this will be called maneuvering. And that's then going to be maneuver stalling speed. Stalling angle of attack. Next on the list, note that the coefficient of lift must be a maximum, or let me rather put it, it will be at the maximum when the aircraft reaches the stalling angle. Normally it's around about 16 degrees. For all the purists out there, all right, I know about Reynolds number and I know about all the other fancy tricks, and I know that this angle can change considerably. For what you and I, and for basic aerodynamics that we're busy with now, we're going to take that around 16 degrees, and in fact, let's call it 16 degrees, otherwise we haven't got a specific point of departure. That is where the aircraft, for now, we're going to take as the stalling. Now, the speed at which this angle is reached is called the basic stalling speed. And remember, that is in clean configuration. So what I'm saying is that basic stalling speed, or clean configuration, Vs, is defined where CL reaches a max. Now, if you look here at your angle of attack versus coefficient of lift, now remember that's where we say in the lift formula, if you look at lift equals coefficient of lift half rho V squared S, when you look at this formula, note that the coefficient of lift is dependent, as it goes up there, on the angle of attack, or the alpha. All right, now when you reach the critical angle, that will obviously coincide where coefficient of lift is maximum for that particular wing or with that particular configuration. Again, we're not talking flaps at this moment in time. Flaps will obviously change the CL and the angle of attack story a little bit. However, for now, I need you to understand that in this, the speed at which, as we now are going closer and closer to the stall, the coefficient of lift or the angle of attack is going to be increased until a time, well, obviously, if you want to say this is equals to weight, in other words, lift must stay a constant, so lift stays a constant, then we'll see that the velocity has to decrease in order for lift to be equal to a constant. Right. So for now, we need to know that the moment that it reaches the critical angle of attack will then be at CL max. Now this immediately leads then to, again, what we've said here. If you look here, as the coefficient of lift increases, the corresponding speed where max is reached, that is going to be your stalling speed. And we've now come to the point where we're just going to call it Vs. So Vs, our stalling speed. Right. So now we can conclude. And what do we say here? Well, we say that the basic stalling speed, sometimes called VB in the AP3456A, is important as the application speed is the foundation of the next 4 deliveries. Everything is derived from, I said, just last week I said to somebody in here, if there's something I would like you to engrave, okay, now don't go and do a tattoo for that, but the point is lift equals coefficient of lift half rho v squared s. It's the foundation. If you know the formula and you understand where this formula will take you and how important this is for your survival. And a lot of people say to me, but you're scaring all of us because, just remember there are rules. And we just have to stick inside the rules. It's scientific rules. It's not something that you and I can tamper with. So it's important. First of all, we must have the knowledge. Then we must develop the skills to use that knowledge. And then thirdly, you need a very good discipline or a very good attitude in order to apply that. Until the next delivery.
We hope you enjoyed that aviation snippet with Charlie Murray. Please make sure to visit our website www.aviationauditing.co.za. Follow us on both Facebook and Twitter and subscribe to our YouTube channel under Seams Studio.